Okay, so more on these stream functions are things that we can calculate which are called streamlines. So there's a stream function that I'm going to say exists. It's really a function of x and y. And then we have things that are called streamlines, which are where this function is constant. So like sometimes, right, classic ones will look like this. I mean, it can be anything as a thing, and you can graph them, or this, right, all the points x and y here, xy points in space, this could equal one constant, another one, and another one. So really these are contour lines of a surface living above the xy plane, but we call them streamlines. And they help you visualize the flow, because if one point's along here, it will just kind of go along for the ride. But there are other things that we can talk about these streamlines, and that has to do with flow rate, and it makes flow rate a pretty simple calculation. So, right, first you look at a little bit of change in the stream function, right? We do the same linearization thing that we've done before for all of the vector things we've done. Okay, these have definitions to them, right? So this was v dy, and then the other thing you say is if I'm along a streamline that's constant, then there's no change in this function value. All that's changing are these quantities. So this I know to be 0 because if I'm on a streamline, equals k there, still equals k there. So this being the change. So that gives us a way to plot streamlines once you have the stream function, and they represent, right, this classic relationship. Okay, so you can plot out lines where the curve, right, the slope is related by the ratio of these velocities, and that can help. So there's a picture in the book, and in the notes, but what I'd like to do is just really the simple calculation it makes for flow rates between two stream lines. So here's one streamline, here's another streamline. So I'm going to call this one 2. Okay? So the flow rate per unit width, because I've divided out that rate, I divided out this z direction because it's two-dimensional incompressible flow. The flow rate, I'll have a qx and a qy. So right, this is just saying what comes in must come out. So whatever came in through this arbitrary line I drew between the values of two stream lines is just the summation of these two things. Right? And if you take derivatives of these, so let's like a change in flow rate would be a change in these things. You have dy, and you have a dx. And this is just a definition of the flow rate in the x direction. So I need a velocity in the x direction times this linear area, which is just the dy. Same with this. In the y direction, I need the velocity in the v direction times this area, or this linear area, dx. Both of these would be multiplied by whatever unit width you wanted, and then you get this expression here. Well, this is exactly right. So this is just one connection that we have, and this is the change in the streamlines. So that allows you to say that there is, right, obviously there's no flow rate through one streamline. You need a difference of these two. And really, what Rennie just integrated this relationship where you have then Q, where I go from 1 to 2. And that's just right. That's the best part about the stream functions. You have the flow rate between two streamlines is just equal to the difference. Yeah, so that is one simple calculation you get from streamlines and stream function analysis. As you can see, what is the flow rate between two streamlines that are constant, or two streamlines, which represent values where the stream function is constant. And and you have calculations to get a handle of how actually easy that is, because you just need to evaluate this at a point and then this at a point.